Good afternoon or good morning to my 5 students who are concurrently enrolled in strength and conditioning. I'm sorry I'm a little delayed on this. I'm going to give you guys an abbreviated lecture with regard to the information that we covered in class today. So let's go ahead and turn to chapter 3 slides. And as you're opening those up, why don't I make a few announcements? One of them, check Moodle. I've posted a lot. I'll continue to communicate with this class via email. So check those emails on a regular basis. I should clue you in as to what's happening, and it'll be especially important for this group. If you're having any trouble in working on the homeworks and or the new study guide that I've posted, essentially a majority of the next exam will be on this study guide. Please ask Kyra and myself. Kyra is in her office on Mondays from 4:30 to 5:30, on Fridays from 10 to 11. I'm around during office hours on Wednesdays from 1 to about 2:45. And I'm doing some extra sessions as well to make sure students have all the opportunity needed to make sure you are ready for that exam on the 12th. I'll need to know from you guys, so please talk amongst each other and somebody get back to me within the next day or two. Are you going to miss Ben's class on the 12th and take the exam with my class? Or should I reserve the conference room for you guys to take that exam at 10 o'clock on the 12th? So please advise me so that I can do the right thing about that. I want to go back now to what you're seeing in the slides. And we're going to be talking a lot about norm reference standards. Remember, when we evaluate, we use either norm or criterion reference standards. And the norm reference standards say, how did you do versus some other defined group? How did you compare on your VO2 max, for instance, against other men and women of your age group? How did you compare on your Wingate test scores if you are a champion and a National Hockey League player? You really want to know how you compare. You use normative when you compare against like others, these normative reference standards. And the words that you want to come to mind on slide number 20 are percentile rank. Percentile rank. Make sure you get that down. When you hear norm, we're thinking percentile rank. That's going to be a little bit different than what we're going to do when we do the projects. When we do the projects, we're actually going to create a table like the ACSM normative tables. You're going to figure out what score corresponds to the 100th percentile, the 90th percentile, so that you now will actually create your own frequency distribution chart, but is showing what are typically, each decile of percentile rank, or every 5th percentile rank. What's the 0 percentile, the 5th percentile, the 10th percentile, the 15th percentile. So please be able to distinguish what you do in these cases. Until we do the projects, we're going to be focusing in on percentile rank. And what we're going to do is we're going to say, here's a distribution of scores. You tell me where you stand relative to the other people in that defined group. So percentile rank is simply the percentage of observations that fall at or below a given point in a distribution. At or below. Percentile rankings will go from 0 to 100%, okay? And one of 2 key ways to determine what your percentile rank is to create what we call a simple frequency distribution. So aren't you going to be silly if you go to your boss and you say, hey, I tested all my athletes. Boss, we brought them into the HPL. We got the VO2 maxes on 65 people, and here's their scores. No, don't do it. That's not the way to present data. Instead, if you'll recall, the term statistics means we're going to use the tool of statistics to express and interpret this data in a way that's much more user-friendly than simply, and as you look across here are 65 of what we'll call raw, or you can also label these as observed scores, okay? So it doesn't make sense that we just give all of these raw or observed scores to the head of the PT clinic, the head strength and conditioning coach, when he or she asks us to kind of, hey, how did everybody do? It's not a usable form. These are the raw, or what we call the observed scores. And we're going to create a frequency distribution table that's going to allow us to kind of talk about these scores in a meaningful way. So one of the questions you're going to see on the study guide is, unless you have access, all right, to statistical software programs that are immediately going to come up with the percentile rank for a given score in a distribution for you, you're left with these two ways of determining what is the percentile rank of any score in a distribution. Everybody got it? Two ways to compute the percentile rank in a distribution. Number one, you can create one of these frequency distribution tables or charts. Okay. Again, not using software, but we're going to do it the long way. And then please highlight the word if. If scores are normally distributed, we're going to learn that's the case oftentimes for the kind of data that we collect in large numbers from groups of athletes or patients. There's scores in the middle, there's scores at the extremes, but it follows a normal or what we call bell-shaped curve. If the scores are normally distributed, now we can use the information in the latter part of chapter 3 to convert the scores to z-scores and then determine the area under a normal curve to see what is the percentile rank. But let's go back to this method. This is where we're going to start today. You did this in the homework. You said, I'm not going to just, here's the 65. I'm not just going to give you all these raw data and say, here's how everybody did. It'd be a little bit silly. Instead, you're going to present the data in this form. And you're going to see, for example, that there was 141, there are 11 48s in this distribution, there were 6 51s, etc. When you list all of these scores, it's incredibly important that you go from worst to best. Worst to best. So keep in mind, if you're doing timed runs, okay, for example, how many seconds did it take for you to run the 40-yard dash? A lower score is actually a better score and will appear at the bottom of this distribution table that you create. You write the numbers. You see what is the frequency of each of those numbers. And what I always do at the end is I check to make sure that, in fact, if I count the raw scores, that there are 65 of them, it's the same total if I look at this column that I've created for the frequency of which each of these scores occurred. And you can see there's no 42. It's not included in this distribution chart. I next know that there are 65 people in this group. And I know that 1 out of the 65, I use my calculator, that is 0.015, all right, is the number I get when I take 1 divided by 65. 0.015, okay, 0.015 is 1.5%. Similarly, if I have 5 out of 65 of the scores, if you follow me on the cursor here, that are 45, I have 0.077 as the percent, or simply 7.7% of the 65 scores are a score of 45. This valid percent column comes out on the computer outputs when you're using predictive analytics software, but essentially it's the same as the percent column. You won't be creating this when I'm asking you to do this on exams or quizzes. You will need to say, what's the scores that I see? How often did they occur? What is the percentage of each of those scores? And when you add these all up, you can do a little check to make sure you're on the right track so you don't get this problem wrong. And you should see that 100% of the scores, okay, when we total this up, should be represented in this frequency distribution table. The next and the last column that you really care about is what we call cumulative percent. What that indicates is what percent of the scores are 41 or worse. Well, there was 1.5% of the scores that were 41. Nothing is worse. So the cumulative percent is 1.5%. This next value of 6.2 shows you that 6.2% of the scores are 43 or worse. How did I get that? I took the 1.5% of the scores that were 41, okay? I added to that the 4.6% of the scores that are 43, and I now see that 6.2% of the scores are at a 43 or worse. I'm going to continue to do this all the way down, all the way down. If I've done everything correct, again, another little check for you is that you see here that I should be at 99.9 or 100 at the bottom of this column, because 100% of the scores now were 55 or worse. Okay? We said that when you complete one of these frequency distribution tables or charts, you very easily now can determine the percentile rank. And you're going to see, if I asked you, okay, somebody got a score of 51 mils per kg on their VO2 max. Given this distribution of scores, you can see that their percentile rank is 86.2. So, compared to giving all the raw or observed scores on a piece of paper to your boss, if you create this frequency distribution table, you're going to see all the scores. You can determine the lowest score, the highest score. What was the most frequent score? Okay. Well, let's take a look here. This pops out. The most frequent score was 48 mils per kg per minute. The other and most important last piece of this for our purposes is we use percentile ranks as a way of determining norm referenced evaluation points. So what is the percentile rank, for example, of that score of 51 mils per kg per minute, given the data in the distribution? You have to know how to interpret this. This is a norm reference comparison. We use percentile ranks, and a good way to say this is 86% of the scores were at or below 51 mils per kg per minute. Realize that when we say below, it can be confusing when you have scores like body fatness, all right? These tables are set up so it's really, if you had an 86.2%, it's 86.2% of the scores were worse in terms of body fat, all right, than you were. Doesn't mean that they were necessarily lower values, because lower values is actually better scores. You have to get this interpretation piece down. You must know that these are all correct interpretations for a percentile rank. And hopefully you recognize that we're talking 100 as being a denominator. It's the same thing as saying out of 100 people, you scored better than, or better than, you scored equal to or better than 86.2 of them. And given this is a high number, you're going to be able to put a smile on your face and say, hey, you did pretty good compared to other people. But these are the better interpretations that you should get down. Okay? See this down here? Make sure you take a look at that. We mentioned the other day that if everybody's over fat, just because you're at a fairly high percentile rank doesn't mean that you're necessarily doing well in terms of a percentage of body fat related to health risk. I think we've gone over this slide. Make sure you understand it. Always, my suggestion is to write worse and best when you create these frequency distribution charts. Okay, so we take the data, we can put it into a graphic form. You absolutely have to know that for histograms, smooth distribution curves, polygons, in all those cases, the frequency is what is on the y-axis, and then the individual scores. We mentioned the observed scores, the raw data. There was one person who had a 41, so we've made the height of that bar, the frequencies, that's on the y-axis. The x-axis represents the scores. And now we can see the shape of the distribution. And if the coach is looking at these, he could ask you, hey, I saw the histogram that you created based on the scores on VO2 max. Could you tell me, who was that guy who got a 41? I'm kind of worried about that. They're kind of out of the group. Maybe they're a little bit low and we have to work on training some of their aerobic capacity given this sport is soccer. Okay? So the shape of these distributions are going to be described in two ways. Are they symmetrical or not? And if you follow me on the slide, symmetrical or not, which would be skewed. And are they peaked? Meaning, are they very high and kind of narrow in terms of the distribution, or are they fairly flat? Are they kind of in the middle? So let's look at the histogram, and let's take the midpoint of each of these bars, which represent the frequencies, and let's connect them with a straight line. So we end up with this jagged kind of a line that you see here. This is what we call a frequency polygon, okay? Now, most of the time we smooth this data out, but I do want you to know that you can create what's called a frequency polygon, and you should recognize that it looks like that. Now, you remember bar graphs. Maybe you did bar graphs before. Is a histogram a bar graph? The answer is no. They differ in two respects. With regard to a bar graph, what is on the x-axis is oftentimes categorical, nominal data, or ordinal data. And now the other difference is, all right, we're going to leave some gaps or spaces between the adjacent bars when we do a bar graph, which was not true when we saw the histogram. So, are you personality type A, type B, or type C? Please, somebody tell me, what is the level of the variable of personality type? Is it nominal, ordinal, interval, or ratio? I hope you say it's nominal, it's categorical, okay? And here you see the bars representing the frequencies, all right, with each of these three personality types. So now we're going to smooth that polygon out, okay? We're going to smooth that polygon out, which is very customary when we have this interval ratio data. And we end up with a smooth curve that we need to describe with regards to its symmetry or not, and how peaked it is. So, answer this question. I'm on slide 35. What is on the x-axis in a smooth frequency distribution curve? What's on the y-axis? I hope you put the values are here. And this is the frequency. Always label your graphs, or you risk not getting full credit on exams and quizzes. Always label your axes, rather. All right. First, we're going to talk about symmetrical or not, okay? Distributions are symmetrical, and you see it here. Symmetrical means they're the same on both sides. Put a line down the center. These are mirror images of each other. Skewed distribution deals with the fact that you have some outlier, okay? Maybe your friends tell you you're skewed. You're kind of an outlier, all right? Here we see a distribution, and I'm pointing on the cursor now. This far right edge of this distribution is some of the outlier scores. There's a few people who scored very high on the scale. Please label this as right or positively skewed. Right or positively skewed. This other distribution has a few out in its tail of we call this the tail of the distribution, has a few outliers way out here. This is what we call left or negatively skewed. So one of the ways to describe these curves is to look at this. Does the curve, is it symmetrical or is it not? In which case it's skewed, and we can talk about right skewed and left skewed, positive and negatively skewed respectively. So in this slide, how are we going to describe it? Is it skewed? No, it's symmetrical. So we know that this is going to be a normal curve. It's symmetrical. Both of the sides are mirror images of each other. In fact, we say it's symmetric. And with regard to peakedness, which is the next concept we're going to cover, it's meso. It's in the middle in terms of peakedness or kurtosis. So let's look at some distributions. Here's a normal distribution, positive skewed, negative skewed. I just want to let you know that even though this is kind of symmetrical, okay, you see it's almost like two normal curves here. In fact, we had two very frequent scores. One's here and one's here. These might represent the heights of people at HSU. This might be part of the distribution for women. Here's the distribution for men. There's probably going to be some overlap in this area. We call this bimodal because you've already remembered that the mode is the most frequently occurring score. We can determine the mode by looking at what's the highest peak. In this case, there are two highest peaks. All right, We've described curves in terms of their symmetry or not. Now we're going to say, are these curves very peaked or not? In this case, we have a fairly flat distribution. This is the platykurtic distribution. Here we have a very peaked distribution with the scores being relatively homogeneous. They're quite the same. They're all kind of right there in the middle, whereas this is more flat. The scores are more spread out. This flat curve, in terms of its kurtosis or peakedness, is described as platykurtic. This is what is called a leptokurtic distribution in terms of its peakedness. And what you're going to see here is this is in the middle. This is mesokurtic, or what we see in a normal curve. You can remember the platykurtic by remembering your friends in Australia called the duck-billed platypus, a very flat bill, hence the flat distribution, the very heterogeneous or spread out, not very peaked platykurtic distribution. Okay, so now we're to the part where we're going to talk about the measures of central tendency. You should know there are 3 measures of central tendency and be able to list them: the mean, the median, and the mode. There are 3 measures of what we call dispersion. There are 3 measures of variability. There are 3 measures of spread. Different words for how spread out are the data, and those are the range, the variance, and the standard deviation. So first, let's look, where do the scores tend to cluster? Where do the scores tend to cluster? We determine the mean as the arithmetic average of the scores by summing all of the raw data, all of the observed scores. We're going to sum them up, and we're going to divide by how many scores there were. Okay? So every score is used to determine the mean. It's very often used measure of central tendency, particularly for interval and ratio data. I oftentimes ask my TAs, hey, what was the mean on the quiz? I want to know how they did. So that's the mean. You guys know it. You've had it since 2nd grade. Beware, beware, beware. Memorize this rhyme. The mean is pulled to the extreme. The mean is pulled to the extreme. Okay? Keep this in mind. Very, very important. The median, on the other hand, you should recognize as the position of a score such that half or 50% of the scores are lower than that score, and half of the scores are higher than that score. This is the middle score, and it's based on position. We're actually not looking at the numbers so much, but where are you in the position of scores? So, what is the median of these scores? Well, you order them in order. 2 would come first, 3 would come next, 4, 5, okay, 9. Is that what's next here? Did I do 2, 3, 4, 5, 9, and then you're going to list another 9 and 11. You should, when you list these in order, show that there are 7 scores that you're listed out. That in this case, that number 9 got repeated twice. When you list them in order from smallest to largest, it's going to be clear that 3 scores are higher than a 5 and 3 scores are lower than a 5. So the median here is actually going to be a 5. What happens, though, when you have an even number of scores? You can't divide by 2, can you? Well, what you do is you do this. You go 1, 2, 3, 4, 5, 6, 7, 8. There are 8 scores. You add 1 to it, which would make 9, and you divide by 2, and that would tell you that the position of the median score would be the 4.5th score from the end. In this case, you're going to have scores that are in the middle, meaning there are 2 scores. One's going to be in the 4th position. One's going to be in the 5th position. You're going to average those 2 scores to find the median. Make sure you know how to do that. And the mode is the most frequently occurring score. Okay, here we have a bimodal distribution. You could say there's a mode here at what is it, 8.5. There's another mode here right around 5.5. Okay, it's the most frequently occurring score. I've told students they need to memorize this. This chart is huge and important. A lot of the data we're going to collect in this class is interval ratio data. Okay? If you have a normal non-skewed distribution, the mean works fine in telling you where the scores cluster. So that would be a very good measure of central tendency. But if you have positively or negatively skewed data, we want to go back and we want to remember this beware. Beware that the mean is pulled to the extreme. So when you have skewed data, numbers are going to be pulled out to one side. The center of that data, indicated by the median, is the best way to summarize where do the scores cluster around. Where is the middle point? The median is the best measure of central tendency in two instances. When we have interval ratio data and the data is skewed, or when we have ordinal data, the middle position or median is the best measure of central tendency. If I asked you how many Republicans, how many Democrats, how many independents, if more people in this class were independents based on the category, that would be the mode. Okay, I'm going to tell you that most people, where things kind of center, is around being of the independent party as opposed to Republican or Democrat. So this is where we're going with this. If we have what's called a normal distribution of scores, it's sometimes called the bell curve. You should know that this curve that you're seeing in slide number 47 is mesokurtic. It's not platykurtic, and it's not leptokurtic. And you should also note that this is symmetrical. It is not skewed. If we have a normal curve, it turns out that the mean, the median, and the mode are all going to be at that very same point in the center of that distribution. The other thing that's so wonderful about this curve, when we smooth out these histogram kind of data and we collect it on a huge number of people, we see that most people score in the middle and then people score out here in the extremes. What you will notice in this curve is that 100% of the scores are indicated in the area under this curve. Given that it's symmetrical, we're now going to, if we know that it's normal, be able to figure out what percentage of the scores fall within a certain range of standard deviations here. That's where we'll be going in class on Wednesday. And we will be doing a lot of the sample problems that are posted for you on Moodle on the handout that deals with the normal curve and standard scores. One last point, I mentioned that when you have a skewed distribution, which is the better or the best index of the center or where the scores cluster around? What is the best measure of central tendency? Well, in this skewed, called left skewed, is this positive or negative? Negative. You look for where the tails are. Where are the extremes? They're to the left. This is a negative distribution because scores theoretically are going to increase as we go out in this direction. So where is the mode? It's going to be the highest point with regard to frequency. This is a bad slide. I didn't label frequency here, and I didn't put scores down here. But what I want to show you is the fact that the mean is not a very good index of central tendency when the distribution is skewed. Okay? So, for example, I'll do an example in just a second, but I want to say the dictum again. Memorize this. Memorize this. The mean is pulled to the extreme. The mean is pulled to the extreme. So when you have extreme scores, the mean is going to be pulled in that direction, and the median is the best index of central tendency. So I don't know if you guys ever watched Jay Leno, but Jay Leno was a collector of antique cars, and he loved antique cars. He had one of the most extensive collections that was around. And let's say Jay Leno finds the perfect old car that he wants to buy. And the dealer who wants to sell him this car, all right, tells him, all right, he's going to try to sell him. He's going to say, hey, man, all right, the mean price on these cars, all right, is $50,000. Okay. Now, if Jay Leno were to buy that car at $50,000, would he be getting a great deal or not? Well, the answer is, if the distribution looked like this, the mean is being pulled towards the low end of the scale. If he were to pay $50,000 for this, he's actually getting a really good deal, because a few of the cars in this distribution had very low values, so the mean is pulled to the extreme. A fairer price would be the median. That's the midpoint for cars of this year, model, and make. It is more representative of what is a correct price for that car, so Jay Leno would have gotten a great deal. The opposite example of this happens oftentimes in the sale of real estate. Imagine now that instead of a left-skewed negative distribution, you had a distribution of home prices that went way out here to the right. Why? Because one of the homes, I'm off the scale here, sold for $1 million. But most of the homes sold for $400,000. The mean is pulled to the extreme, so the mean in a right skewed curve is going to be way out here. So if the realtor told you, hey man, the average price of homes in this neighborhood that's selling is way up here at $750,000, maybe you should offer that. That wouldn't be very fair, because maybe there was $1 million home that sold for $750,000, but most of the homes were selling back here at $450,000. You can see that the mean being pulled to the extreme, you wouldn't want to buy a house for the mean. Fair value for that house is more represented by the median home price, because it's not pulled out to that extreme value and is more representative of the homes in that neighborhood instead of that one crazy outlier $1 million home. So practical implications for all of you when you go to buy a house. All right. So this is the way we indicate it. In this example, the mean is pulled to the left. So it's the smallest value. The median's in the middle, and the mode is, if it was indicated here, would be here on the scale. There are 3 measures of variability. The range is easy. It's the difference between the highest and the lowest score. The variance and the standard deviation are kind of indices of the spread or variability that are oftentimes used, particularly the standard deviation. We won't talk as much about variance in terms of practical tools until we get to the unit on research. But variance is based on the squared deviation of each score from its mean. Okay? The standard deviation, memorize this, represents the average variation from the mean. The average variation from the mean. What I want you to do is take a look at the email that I sent to the entire class, complete the salmon colored sheet, turn it in at 8 o'clock on Wednesday, and you will get 2 points of extra credit. I'll add them maybe to your exam score. And so I want you to understand how these concepts are derived. You can start with the variance and go to the standard deviation. We'll pick up here on Wednesday, and we'll do a lot of sample problems that are related to the material in the last part of chapter 3. You guys have a good day. Thanks.